If I told you that the fluffy white cloud floating above your head weighs as much as 100 elephants, you might laugh. But it's true. A single medium-sized cumulus cloud can hold hundreds of tons of water, and yet it drifts lazily in the sky, as if weightless. If you filled a giant tank with that much water and tried to hold it above your head, it would crash to the ground instantly. So why doesn't the same thing happen to a cloud? Why doesn't it plummet down in a watery disaster? This is one of those questions that sounds simple, but the answer completely changes the way you think about air, water, and even weight itself. The first step is to realize that clouds are not giant blocks of water floating up there. They are made of tiny water droplets and ice crystals, so small that each one is measured in micrometers, millionths of a meter. These droplets are light, yes, but not massless. If you put them all together, the total mass is enormous. So how do they stay up? Imagine you're standing in a swimming pool holding a handful of sand. If you drop it, the grains sink quickly because they're dense and heavy compared to water. But now imagine those grains are replaced with tiny fluffy pieces of pollen. They drift downward very slowly, almost floating in place. The reason is that the surrounding fluid, in that case water, offers resistance, a drag force that slows their fall. The same thing happens in the air with cloud droplets. Air is a fluid too. We don't usually think of it that way because we can't see it, but it behaves exactly like water in many ways. The tiny droplets that make up a cloud are so small that the drag force from the air almost perfectly counters the pull of gravity. They fall, but incredibly slowly, mere centimeters per second. And here's the clever part. While they're drifting downward at that snail's pace, they're also riding on rising currents of air. Warm air near the surface rises because it's less dense than cooler air above it. This rising motion, called an updraft, acts like a conveyor belt, lifting the droplets faster than gravity can pull them down. As long as the updraft is strong enough, the droplets remain suspended and the cloud stays in place or even grows taller. This is why clouds often form on sunny afternoons, when the ground has warmed up and convection currents are strongest. The cloud is essentially the visible top of an invisible fountain of rising air. Let's use an analogy you can feel. Picture holding a feather in front of a fan. The feather is heavier than air, so if you drop it without the fan, it falls. But turn on the fan, and the upward rush of air can hold it in place, or even push it upward. In the sky, the fan is warm air rising from the ground, and the feather, that's each individual water droplet inside the cloud. Now, you might be wondering, what about the sheer weight of all those droplets combined? Doesn't gravity care about the total weight? Gravity indeed pulls on every droplet, but here's the trick. The droplets are spread out across kilometers of sky, each supported individually by the updraft and air resistance. There's no single block of weight for gravity to pull down at once, the way it would with a bucket of water. The result is that the cloud's total mass is enormous, but its parts are each light enough to be supported. But clouds don't float forever. Eventually, the droplets inside them can grow larger. This happens when droplets collide and merge, or when water vapor condenses onto them, making them heavier. At a certain size, usually around a few tenths of a millimeter, the drag force from the air can't balance gravity anymore, and the droplets start to fall as rain. That moment is like the point when a balloon can no longer stay aloft because you've added too much weight. It suddenly sinks. Until then, the droplets just keep surfing the air currents high above us. The aha moment here is realizing that clouds are not weightless at all. They're heavy, but they float for the same reason a dandelion seed can drift on the wind while a stone cannot. Size and density determine how gravity and air resistance interact. A cloud is really just a massive, slow-motion balancing act between gravity pulling down and rising air holding up. And once you see it that way, you understand why clouds have such variety. Thin, wispy cirrus clouds form high up, where the air is cold and the droplets are mostly ice crystals, tiny and easy to keep aloft. Towering cumulonimbus clouds, the giants of thunderstorms, form when powerful updrafts carry huge amounts of moisture high into the atmosphere, building cloud towers taller than Mount Everest. In both cases, the same principles apply. It's just the scale and strength of the updrafts that change. Here's another fascinating twist. Even though clouds float in the air, they can actually make the air underneath them cooler. The droplets block some sunlight, casting shade on the ground, which can reduce the surface temperature and weaken the very updrafts holding the cloud up. That's one reason why clouds sometimes dissipate after a while. They literally cut off the energy source that's keeping them alive. And just like that, a cloud can vanish into thin air, its droplets evaporating back into invisible water vapor. So the next time you look up and see a massive cloud hanging in the sky, remember, it's a delicate, ongoing negotiation between rising air and falling droplets. It's the invisible air currents doing the heavy lifting, one droplet at a time. That serene, gentle-looking cloud is really a masterpiece of physics at work. And once you understand that, you'll never see a floating cloud the same way again. Another layer to this mystery is that clouds are never static. Even when they look frozen in place, there's constant motion inside them. Air is flowing up, down, and sideways. Droplets are forming, evaporating, and reforming in fractions of a second. Think of it like a bustling city seen from far away. It might look still, but up close there's movement everywhere. This dynamic balance is part of why clouds can float for hours. The weight is real, but so is the constant renewal of the tiny droplets that make them. This balance becomes even more fascinating when you realize that cloud droplets are not all the same size. Many are so small they're essentially weightless in terms of how they interact with air. Others are on the verge of being heavy enough to fall. It's a distribution, a spectrum, and the updrafts can handle most of it until conditions shift. When warm, moist air stops rising as fast, or when the droplets grow larger due to more condensation, gravity starts to win. That's when rain begins. In a way, rainfall is the cloud letting go of the extra weight it can no longer carry. There's another important point. The weight of a cloud is measured relative to air. If you were inside a cloud, and you have been every time you flew through one in an airplane, you wouldn't feel crushed by the mass of water. The droplets are dispersed in air and your body is already adapted to air pressure all around you. In fact, walking through a cloud feels just like walking through fog at ground level. Fog is really just a cloud that's decided to form close to the surface. Same physics, different altitude. So, in essence, the reason clouds don't fall is not because they're light, but because of scale and structure. They're vast collections of tiny droplets, each individually supported by the same air we breathe, riding on currents we can't see. And while gravity is always pulling down, air is always pushing back, just enough to keep most of those droplets suspended. Now here's a perspective shift that might give you a wow moment. The same principles that keep clouds in the sky also apply to tiny particles of dust or pollen floating in a sunbeam. That shimmering column of dust you see in your living room? Those particles are small enough that the movement of air, currents from your breath, heat from the floor, can keep them aloft for minutes or even hours. Clouds are just that same effect on a colossal scale. The next time you see a massive cumulus cloud, imagine it as a gigantic slow-motion snow globe. Inside, trillions of droplets are gently moving, supported by invisible streams of air. And just like shaking a snow globe can make the flakes swirl longer, strong updrafts from the ground can keep a cloud alive and floating far beyond what you might expect. There's also an elegant irony here. The very process that builds clouds also seeds their downfall. The more moisture a rising current carries, the bigger and heavier the droplets can become. Eventually, they pass the tipping point where air resistance and updrafts can't hold them anymore. And when that happens, the cloud stops being just a cloud. It becomes the source of rain, hail, or snow. This cycle is nature's way of moving water around the planet. It's part of the water cycle, a system so efficient that the same water molecules falling as rain today might have been part of a cloud over the ocean last week. Understanding why clouds float isn't just a neat science fact. It's a doorway into understanding the delicate balance of Earth's climate. Clouds control how much sunlight reaches the surface and how much heat escapes back into space. They're central to weather patterns, agriculture, and even how we experience a summer afternoon versus a winter morning. They may look gentle, but clouds are powerful climate regulators. And here's the takeaway that sticks. When you look up at a cloud, you're not seeing a static object. You're seeing a living system of motion, balance, and transformation. Its ability to defy gravity is just the visible tip of a deeper truth about how matter and energy move in our atmosphere. Once you see that, you realize the sky is never still. It's always at work, always negotiating between forces we can't see. So, next time you're lying on your back watching the clouds drift, picture the invisible elevators of air carrying trillions of droplets. Picture the tug of war between gravity and motion. And remember that the piece you see is the product of constant, invisible activity. And if you've just had your own aha moment about those floating giants, you'll know exactly why we love making these videos. Because the world is full of hidden mechanisms like this, things you've looked at 1,000 times but never truly understood until now. So, like this video, share it with someone who still thinks clouds are weightless, and subscribe to How It Actually Works. Your curiosity is the wind, and we're here to keep it lifting you higher.